So I'd like to welcome people today to the June 24th meeting of the GLIMPRINT mini seminar series. As always, I need to remind people that this meeting is live streamed and recorded and made available afterwards in edited form. I want to remind you that GLIMPRINT is a membership organization. We would love to have you join us. Individual members are $100 a year for senior people and $10 a year for students. If you would like to join us, please go to the GLIMPRINT website and join us. We're also definitely looking for more volunteers and officers for the organization to help us build it up. If you know anyone who would like to be an institutional or corporate member, we would appreciate your help there too. We're trying to get the resources in order to have a in-person annual meeting and have some additional events. And so your support would be much appreciated. We have a set of social media websites, and there's also a LinkedIn page for GLIMPRINT as well. So suggestions for content, whether you want to announce a paper that you've published, a workshop, a job opportunity, funding opportunity, anything that's relevant to the community, we can post there. If you want to do it yourself, there are tools for doing that. If you need help doing that, we can help you with that as well. So here is publications. At the moment, Ellen Guardakis is going to be handling that. Ellen mq@iu.edu. You can email her. She can help you get your announcements up on the IMAG page and also on the GLIMPRINT page. At the moment, we do not have a seminar scheduled for July 2nd. July 9th, we have a talk on computational modeling in the future of preclinical research. July 16th, we have another lessons learned talk, lessons from COVID-19 on data trust and decision-making. July 23rd, we have a digital twin talk from Toronto General Hospital. We are not planning on holding meetings in August, and then we are probably going to be moving the time of this meeting from its current slot to a little bit later and moving it from Thursday to Wednesday. We'll finalize that in the next day or two, and we'll make sure everybody has the announcements for that. But we already do have some people scheduled for September, therapeutic targeting of oligodendrocytes, and also Jupiter Algorta, data-driven model of polarity reversal in migrating cells. Jupiter won the Open VT Prize for most reproducible model this year, and that's why he's speaking for us. And if you have suggestions for speakers, please email Lorenzo Vischini at gmail.com. He's very effective at getting people on the books. You've heard me say it before. Suggest yourselves, suggest your students or your postdocs. It's okay if you spoke before, if you have something new to talk about. And also, if you have heard anybody that you would like to hear speak here, read a paper, people can be in the area of immune digital twins very, very broadly. They could be developing general digital twin technology. They could be working in weather forecasting. They could be working in pharma or biotech or medicine. Anything that interfaces with immunology, deployment of immune therapies, the scaling up of technologies, or digital twins or modeling generally. All of these are fair game. We've had journalists speak. We've had people who are historical or philosophical in perspective speak. Please think broadly about what would be interesting to hear for this community. So today we have Yue Liu from Purdue talking about optimal experiment design for practical parameter inference. And I will turn the screen share over to him.
Hello, everyone. My name is Yue Liu. I'm a postdoc at Purdue University currently, but I'm moving to Duke very soon. I'm very glad to be here at this seminar to talk to you about some issues about experiment design, parameter identifiability, and model selection, which is a part of my PhD and postdoc work. So let's consider the situation that when we have a mechanistic model, right, we tend to have parameters in the model whose values are unknown a priori, and we have to determine them by fitting the model to the data. So here I have this very simple example where we have a logistic growth model, and you want to fit it to the time series of the population of, let's say, some bacteria or some cell you have growing in your dish, right? And in this example, you can clearly see that the red line corresponding to R equal to 0.7 fits the data better than any of the other lines. And indeed, I have generated this synthetic data with R equal to 0.7. So if you have a error model on top of your mechanistic dynamics model, you can plot something called the likelihood function that tells you that 0.7 is the most likely value for R. And in this case, you can be pretty certain that the true value of R is around 0.7. However, a problem arises if this best fit value is not unique. So if I just extend this model by adding this gamma parameter here, which allow you to fine tune the effect of this carrying capacity on your population growth, then you can have a series of model solutions produced from very different parameter values, but they all fit the data approximately quite well. So in this case, if you plot your likelihood, right, the likelihood says, well, gamma is probably above 1, but beyond that, you can't tell what's the true value of it. So in this situation, these parameters are said to be practically non-identifiable. And this non-identifiability problem can also be reframed as a model discrimination problem. So suppose that I have this extended model with the gamma parameter, right? And I have my best fit parameters here. I have the simpler logistic growth model, and I have my best fit parameter here. And I try to plot them, and the solution looks about the same, right? The solutions are indistinguishable. In this case, I'm not sure which model is the right one, right? So identifiability problem is related to the problem of model discrimination. The problem of parameter identifiability has not received a lot of attention traditionally, right? Traditionally, people say, well, my data fits my model fits the data, so all is good. But I would like to argue that parameter identifiability is important. So consider this situation where we have data from t equals 0 to t equals 0 to t equals 10, and we have two models here that agrees with each other and the data really well up until that point, but they diverges past t equals 15, right? So in this situation, we can't really tell which one is the right model. And if we just took our best fit model, which could have been either one of these, and make predictions based on that, we could end up saying very wrong things past t equal to 15. Which means practical identifiability is important if we want to ensure that our model predictions are reliable. It is also important if we want to make sure that the mechanistic insight given by our model is reliable, right? So for example, consider the situation where we have a gene regulatory network with 3 genes, right? Model 1 says A promotes C both directly and indirectly via B. Whereas model 2 says B is not involved, A just directly promotes C, right? these two models, if you fit them to some noisy data, can give you the exact same model solutions. You cannot distinguish them if you cannot observe B, right? Let's say your experiment just measured A and C, you cannot distinguish these two models, which means if you were to try to draw some conclusions about the role of B in the system, you can't do so reliably. Right, so identifiability is important. So what can we do if we have a model that is non-identifiable? So because identifiability is a property of both the model and the data together, we can tackle this problem from both fronts, right? From the model side, what we can do is we can ensure the structural identifiability of the model. So what this means is that we can make sure that our parameters in the model do not compensate each other exactly. In other words, we do not have redundant parameters. Second, what we can do is we can reduce the complexity of the model, right? And I'm going to talk a bit about that in section 1 of this talk. Another thing we can do is reparameterize. The idea is we can combine non-identifiable parameters into identifiable combinations of parameters, right? From the data front, what we can do is optimal experiment design. Some of the basic ideas are, let's just increase measurement frequency or resolution, right? Obviously, more data is better. However, there are more, if we can't always do that, there are more we can do on the experimental design front. We can choose, for example, better things to measure, right? And we can add an external stimuli to the system such that this stimuli would probe the system in a way that allows you to observe more of it. And I'm going to talk about these two in later sections of the talk. Right, so the rest of the talk is going to go like this. So in section 1, I'm going to talk about the effect of model complexity on parameter identifiability. So in this section, we assume that the experiment and the data are fixed, but we get to choose the model. In the second section, I talk about ways of characterizing spatial data to extract more information from the same data set, right? So here, the experiment and the model are fixed, but we get to choose how we deal with the data. And in the last section, I talk about optimal experiment design, which is the advertised portion of the talk, but I think the two previous section is a good lead up to this. So in this section, we talk about how to design an experiment such that the data it produces is as informative as possible. So this part is comes from a section of my PhD work. The idea is we have some data and multiple alternative models of varying complexity. We want to see how an increase in complexity affects the identifiability of the model and to quantify how much data we need to support the complexity in the model. So first, before we can talk about identifiability, we have to talk about inference, right? How do we actually estimate the parameters, both the parameters themselves and our uncertainty in those parameters? So on one end, we have something like a maximum likelihood, which is relatively cheap, but it's not informative enough for our purpose. On the other hand, we have Bayesian inference, is much more informative, but it's expensive. For this section, I'm going to use something called the profile likelihood. So we're going to use so the profile likelihood method is built based on the ordinary likelihood, right? So suppose that the status are the model parameters, and and if we assume a Gaussian IID noise in our data set, we can define likelihood in this straightforward way. And the maximum likelihood estimator is simply taking the max of, this should be argmax, so taking the max of this likelihood function. The idea of the profile likelihood is that we want to obtain a approximation to the marginal likelihood of one parameter at a time. So let's say I'm only interested in the parameter theta 1 for now. What I'm going to do is I'm going to take the max of the likelihood function over all the other parameters, so that the profile likelihood function is a function of one parameter only. And I normalize this function basically by the max of the maximum likelihood, so that the maximum of the profile likelihood function is at 0. And a result is that under suitable conditions, we can estimate the 95% confidence region for parameter theta 1 as the set where the profile likelihood function lies above the value of minus 1.92. Okay, so this gives us a way of obtaining a confidence region for the parameter, and we can use the size of the confidence region as a measurement of its identifiability. Okay, so what does the profile likelihood function looks like? So I have here plotted 5 examples. In the top 2 examples, we have a nice parabolic curve. So these 2 examples, they're both telling us that the parameter theta is somewhere around 5, although in this example, we're much more certain that it's probably really close to 5, whereas in this example, it says somewhere around 5, but could be off by quite a bit. Whereas in the bottom 3 example, the profile likelihood curve does not look like a problem, right? In this example, we have a flat top, which means we cannot distinguish the effect of the model of the parameter on the model solution at all, right? The solution looks exactly the same as we vary this parameter. Here we have the profile likelihood curve lie above the critical minus 1.92 threshold, which means the confidence region for the parameter is unbounded. And finally, if we have a bimodal distribution, this tells us that we have 2 competing hypotheses of where this parameter might actually lie, and we can't tell between those, right? So I'm going to call the top 2 situation practically identifiable, and the bottom 3 situation non-identifiable, right? My criterion is, I call it identifiable if the curve is unimodal and the confidence interval is finite. So we're going to, as an example, look at a set of experiments from a barrier assay experiment. So the barrier assay experiment has some cells growing on a dish, and over the course of about 3 days, we watch these cells spread out and colonize the rest of the plate. We have 77 images, and the images are 20 minutes apart. So the study is about, can we quantify cell proliferation and cell motility by looking at these images? And we're going to consider 4 PDE models for this system of varying complexity. We have the standard Fisher equation, which has a diffusion and logistic growth, and we can progressively add more complexity to this model to allow for more flexibility. And so this raised the question of model selection, right? Which model should we use? So the classic selection criterion are AIC and BIC, which says you should pick the best fit model, but penalized by the number of free parameters you have, whereas the M here is the number of free parameter, right? But these criterion are not informed by parameter identifiability, and I believe parameter identifiability is important for model selection. Okay, so let's compute the profile likelihood for these four models and see what they look like. And we can see that for all parameters in all four models, if I use all the data that I have, which is 77 time steps, I have nice parabolic curves for all of them, right? So this tells me that they're all identifiable if I have enough data. What's interesting is what happens if I reduce the amount of data I use in my inference. So the blue curves, NT equal to 77 is when I use all my data. Purple curve is when I use only 20 out of the 77 images. And the red curve is when I only use 3 images, the beginning, the middle one, and the end, right? So how much can I still infer about the parameters if I use a very low amount of data? So it turns out for the simplest model, the standard Fisher equation, uh, I retain identifiability even when I use very little data, right? We can see the red curve stay a nice parabola, even if it gets wider, right? And that's expected because the less data we have, the more uncertainty in the parameter value we should expect, and there is a nice relation you can derive between the two. However, for the more complicated models, when you decrease the amount of data past a certain point, the model just breaks. In the sense that the parameters becomes practically non-identifiable. For this model, the Richards-Gross model with a gamma in it, the profile likelihood curve begins to look like this, and it stays above the critical line as gamma goes to infinity, which means the confidence interval is now infinite. And for this other model, for the parameter beta, when you have very little data, we have a bimodal posterior distribution, right? It says beta can either be around 0.5 or around 1.5, and we just can't tell from the data. So what does all of that teach us? So I hope I was able to convince you that parameter identifiability is important for ensuring the reliability of both predictions and mechanistic insights of the model. More complex models tend to require more data to be identifiable, and therefore the complexity in your model should be justified by the amount of available data you have. And I will leave this section with a quote from von Neumann, who says, with 4 parameters, I can fit an elephant, and with 5, I can make him bigger his trunk, right? So the idea here is that the model fits the data, just being able to fit the data is not good enough. We need to ensure that the parameters that fits the data is unique. Okay, so that was section 1. For section 2, we're going to look at something slightly different. So for section 1, we were looking at PDE models, but for section 2, we're going to look at agent-based models of spatial pattern formation. So the idea of this paper, which was done as a part of my postdoc work, is that in models of biological pattern formation, we can have spatial patterns that are highly complex. And with agent-based models, because the model has discrete agents rather than continuous density fields like you have for PDEs, we require some very different ways of dealing with the data. And in this talk, I'll talk about one way we can characterize a discrete spatial data coming from an agent-based model and extract useful information from it. So as an introduction, zebrafish are a widely used model organism across many different areas of biology. And we're interested in zebrafish because they produce these highly consistent patterns on their skin, right? So the zebrafish, we consider 4 genotypes. So the wild type zebrafish have 5 types of pigment cells on their skin, and they interact to form these complex patterns. In these 3 mutants, 1 or 2 types of the pigment cells are missing, and they form a qualitatively different pattern. So the idea is, can we use an agent-based model to study this phenomenon and infer the mechanistic parameters in this model? So we're going to take the agent-based model from Volkening and Sandstede from 2018. So this model models the individual cells as agents. They move and behave autonomously according to simple rules. So the rules includes movement. For example, the agents can either attract or repel each other depending on their cell type. We can have new cells appear by differentiation, and this differentiation is modulated by the number of their neighbors. And finally, we can have cell type transition, where cells of one type can decide to become another type. And again, this transition is modulated by the number and type of their neighbors. So this is a very different type of model from PDE models, right? So how do we infer parameter in such models? So parameter inference here has 2 main challenges, right? Challenge 1 is that our likelihood function is completely intractable and our simulations are expensive, right? Which means we cannot use something like profile likelihoods as we used before. Challenge 2 is we don't have a straightforward way to compare patterns, right? So let's say I'm asking you, what's the distance between this pattern and this pattern? It's not clear how we can quantify the difference between such patterns, right? And our solution to these 2 challenges, for the first one is we're going to use a method called ABC. And for the second one, we're going to use something called topological data analysis to characterize a spatial pattern. Okay, so a very brief word about ABC. So ABC is a inference method based on sampling, right? So this idea is based on rejection sampling in Bayesian inference. The idea is basically you generate a lot of samples from your prior, you keep the ones where the likelihood is high. The approximation comes in when you don't use the actual likelihood, but you replace the likelihood by a distance function between your model output and your data. So the idea is that if your model output looks like the data, then the likelihood is probably high. So you should keep those parameters, and otherwise you reject them. So this way you can obtain an approximate sample of the posterior. So the problem now reduces to how do we define this metric in pattern space. And that is not trivial, right? So suppose I have these 2 patterns. Your first intuition might be to compare them pixel by pixel, but that doesn't work because it doesn't respect the qualitative essence of spatial patterns. Moreover, the model is stochastic, right? So if you run the model twice with the same parameters but different randomization, you get these two very different looking patterns pixel by pixel, but qualitatively they're the same pattern, right? So how do you extract information from that? So traditionally, people use something like summary statistics. For example, you just go count the number of cells, or there's something called pair correlation functions that also work quite well. But as an example today, I'm going to introduce topological data analysis, which is a good way for summarizing topological and geometric information. So TDA revolves around a concept called persistent homology. So imagine we have this data set of mostly a point cloud data set of cell positions. We can draw balls of size epsilon around each cell and create a graph on these points where we add an edge if their balls touch, and we don't have an edge otherwise. And once we have a graph, we can look at the topological features in the graph. For example, we can look at the number of connected components or the number of loops in the graph. The key insight here is that we can vary this epsilon parameter. And the most important features in the data should continue to be reflected in the graph for a wide range of epsilon. So if it persists for a while for a wide range of epsilon, it's probably an important topological feature in the data we have. Right, so what we have done is we built a pipeline where we take the pattern produced by the model, we compute persistent homology, and we vectorize the information contained in the persistent homology via something called persistent landscape. So the persistent landscape is a set of curves that robustly encodes the topological information in the spatial pattern, right? And by robust, I mean if you move each cell by a little bit, the persistent landscape curves also change by just a little bit. And this means we can compare two different patterns by comparing their persistence landscape curves via the L2 distance, right? So we have a robust way of comparing patterns. So as a demonstration of how this works, suppose we are looking at this rule in the model. So the rule says a new black pigment cells can appear at a random location if the number of golden cells and gray cells in the neighborhood is greater than alpha plus beta times the number of black cells in the neighborhood. So what this is saying is that golden cells and gray cells promotes the appearance of new black cells and existing black cells inhibits it. The parameters we are interested in is alpha and beta. With our analysis pipeline, we were able to combine information from multiple experiments. So remember, we have 4 fish genotypes. So we have at least 4 sequence of 4 time series of patterns. By combining all those information together, we were able to obtain a tightly constrained posterior for alpha and beta, which means we were able to estimate these parameters very accurately. The combination of information from multiple choices is not trivial, and we discuss that further in the paper. So if I look at a more complicated set of rules, so it's not important how what exactly the rule is doing. The important bit is that we have 2 set of Boolean rules with 6 parameters, right? And if we set any of these parameters to 0 or infinity, we can obtain up to 81 alternative Boolean rule sets. And we want to ask, are all of these 6 interactions, 6 clauses in the rule necessary to produce observed patterns? Right, and here is the result of the inference, showing you the marginal posterior for each of the parameters. What's notable here is that for this C tilde parameter, we have a bimodal distribution, which means it is non-identifiable, right? But in this case, non-identifiable is an exciting find because this extra peak in the posterior distribution that we didn't know about hints the existence of an alternative interaction rule set that can produce the observed patterns in the zebrafish that we didn't know about before, right? So throughout this method, what we have done is effectively we have performed model selection among 81 alternative rule sets, and we identified 2 of them that are capable of reproducing the patterns observed in all 4 fishes. And which one of those 2 are correct can be later on determined by experiments, right? So what's the takeaway from this section is that we have built a computationally efficient pipeline for an agent-based model of pattern formation. And the key of this pipeline working is that we're using TDA to characterize spatial data, which is both computationally efficient and effective at extracting geometric information from spatial patterns. And okay, so last section, optimal experiment design. So this is actually the advertised section. So sorry if you feel that I have been swindling you for the past 30 minutes, but I hope you found the 2 previous sections to be a nice build up to this part. Okay, so the idea of optimal experiment design is that let's say we have a situation where we can apply an external stimuli to the system, and we want to design this stimuli in an optimal way such that it probes the system and push it in new regimes that allow us to observe it better. And this is part of my PhD work. So for this section, I'm going to consider a toy problem involving an ODE model, right? So I'm going to consider the Richards-Gross equation, which we have seen before in section 1, right? So that's the one with the gamma parameter. The changes are that I added this term controlling cell death, and I have this U parameter, which is not parameter, it's this U control function, which can represent, for example, the amount of nutrients we're removing from this dish, right? So here C represents cell population on my dish, and I want to use U as a control to better study this model and identify and infer the parameters in this model. Right, as we have seen before, even without the explicit term for cell death, this model is practically non-identifiable, right? I have these 4 model solutions produced with very different parameter values, but they look about the same. So before we can optimize our experiment design, we have to specify what are we going to optimize for. So there are 2 sensible goals. The first one is we can minimize parameter uncertainty, right? We can minimize the size of the confidence region for a parameter of interest. And I'm going to causes identifiability improvement. The second goal is model discrimination, where we want to maximize the difference between two competing models so we can tell which one is right. Okay, so as I have argued before, that these two goals are related, but they are distinct and require separate approaches. So let's consider the problem of optimizing for identifiability first. So let's say, suppose that I want to minimize the size of the confidence region of the growth rate parameter R over all possible piecewise C1 control functions. This is too hard because delta R doesn't have a closed form expression. So instead, to make things simpler, I'm going to restrict my control function to be a window function with height U max and start at tau 0 and with a length of tau. So if I apply this restriction, then I'm optimizing over 3 numbers instead of a function space, and I know how to do that. So now let's visualize what's the effect of applying this control on the profile likelihood curve of the parameter R. So without the control, the profile likelihood curve is completely flat, right? It's flat because a change in parameter R can be perfectly compensated by a corresponding change in the other parameters, which means I cannot tell at all where's the true value of R. However, if I use a non-zero control function, that's going to affect the profile likelihood curve in various ways. Sometimes I still have practical non-identifiability, right? So the curve lies above the critical threshold as R goes to infinity. But in this case, for example, I can very confidently identify the value of R if I pick my control function in a good way. So let's see, how should then what would be a systematic way of picking the control function? So here I have plotted the size of the confidence region against U max, the height of the window, tau, the length of the window, and tau 0, the starting point of the window. What this graph tells us is that basically the stronger the control, the more effective it is at telling us what the system is doing, right? So the story here is simple. The story here about tau and tau 0 is a bit more complicated. It's telling me that I have a optimal timing that I should apply my control for. Not too long, not too short, not too early, not too late. So to visualize that further, I'm going to plot delta R as a bivariate function of tau 0 and tau. And here I can see I have two local optima, right? I can either start my control at about t equal to 8 and run for a length of about 12 period time unit, or I can start my control at t equal to 20 and run it all the way to the end of the simulation. What this tells us is that the timing of the control is important. And in fact, if you look at the local sensibility analysis, local sensibility analysis provides you a good heuristic about the timing. The idea is with the control on and off, you can observe the system in two different states, right? And the control in our model modifies the carrying capacity, and the system is sensitive to the carrying capacity only in the later half of the simulation, which means we want the control window to cover roughly half of the window of the time zone where the system is sensitive to the carrying capacity such that we have enough data from both states of the system. That is what we can do to optimize for parameter identifiability. Now let's consider the other goal, which is model discrimination. So let's say I have two models, right? For the first model, so this one is the same one as before. The second model, I'm setting the delta parameter to 0, right? The second model says, I don't believe my cells are dying. Can we tell between these two models? Without control, we cannot, because the solution of these two models are exactly identical to each other. So how does control help here? So the idea is we want to maximize the difference between the solutions of those two models, right? So so this is difference squared integrated over the whole time period of the simulation or the experiment. So I'm going to penalize the application of control by this alpha U squared term. And furthermore, I'm going to cap the control by some upper bound for biological realism, right? Because in a real experiment, you can't exactly do infinite of anything to your cells. So what's nice about this formulation is that it's set up as an open loop control problem, which we have a very nice tool for solving such problems. So the tool is called Pontryagin maximum principle. So I won't go into very deeply into what this principle does, but effectively it provides us with a numerical algorithm to obtain the optimal control to solving this problem, right? So what does the optimal solution to this problem look like? So in this graph, the purple curve is the optimal control obtained from the PMP algorithm. And but what it basically says is that we should slowly ramp up the control up to around t equal to 10, then abruptly turn it up to maximum, and it stays maximum until the end when we turn it off. If we do that, you can see that the two model solutions, C1 and C2, appreciably diverge once we turn the control on, right? So with sufficiently resolved data, we will be able to tell the difference between these two models if we apply the control this way. So the takeaway of this section is that we are able to greatly improve the informativeness of data generated by an experiment if we design it well. Optimizing for parameter identifiability and model discrimination are related, but they are distinct goals and require separate approaches. So I didn't show you this, but local sensitivity analysis offers a very useful heuristic when obtaining these optimal controls. And we can solve the model discrimination problem via a PMP. Right, so with that, I'd like to thank you for listening and thanks to the organizers for inviting me to the seminar. So I also like to thank my PhD supervisors and my postdoc supervisor. Here are again the references to the papers I talked about. So yeah, that's it. Thank you.
Okay, time for some questions. There was a question from Anil.
How did you decide the weight function is 1 or -1? Sorry, could you clarify which weight function you're talking about?
He says in the integral term.
Yeah, so are you asking if I should have a plus instead of minus here, for example? So the idea of that is, optimal control problem. Usually we want to penalize this solution for applying too much control, right? And that's biologically realistic because a lot of times if we apply our stimuli to the system too much, it would just end up breaking it, right? It would just end up killing all the cells. So by having this minus sign here, I'm saying that I don't want to apply too much of the control. Okay, another question, why do we need to choose the model? I'm biased towards ensemble models. Why not run them all and compare, right? Okay, so this is a great question, right? So for example, if I come back here, so if we have a situation like this where I have some models that could be said to be mechanistic, but are phenomenological to some degree, right? So, for example, this alpha and beta and gamma, they're there meant for flexibility instead of representing something really biological, right? So, if you ask, why can't I just have all four models run an ensemble and do an uncertainty estimate of my predictions that way? So I think you absolutely can, and that's a valid approach. However, if your goal is to figure out exactly how these cells interact, right? So if your goal is to really want to know what's the value of D0, you want to learn how cell motility responds to cell density, for example, then running an ensemble model doesn't provide an answer for that, right? If the parameter values are what you're after, I think ensemble models doesn't offer you that.
I was going to ask the same question Jacob did. And you start out by making a distinction, which we all do, between structural and parametric uncertainty.
Mhm.
But in fact, if you look at some of these models, what you're calling structural uncertainty is also parametric uncertainty. If you set gamma equal to 1, you reduce model to one of the other forms.
Right,
And so there's always some ambiguity about whether it's more a matter of taste, whether you call something a parametric or a structural uncertainty. You can always have some component in your model that has a value of, has a weighting of 0, and that is turning structural uncertainty into parametric uncertainty. I think one question, and you've just addressed it, is what is the purpose of the model? If the purpose of the model is to do forecasting or prediction, then the fact that the ensemble doesn't discriminate perfectly and give you a best model isn't necessarily a problem. It's going to reflect the actual predictive uncertainty. And then when you design optimal experiments, you're going to narrow down the support of the cloud of ensembles that you're working with. But I think one should be careful, perhaps, and this is actually quite a good example of it, which is you have a concept of D0 grad squared C. In fact, cells don't diffuse. The diffusion equation is an approximation to what's happening. It
right,
may be a good or not a good approximation, but in fact, you have the example where you have the porous-Fisher equation, where you're not using a simple diffusion equation, or you're using a modified diffusion equation. And
right,
so D0 as a parameter, the diffusivity of the diffusion constant, is already a coarse-grained approximation of what's happening. And so in this case, there really isn't a choice. You have D0 as a concept in all of them. But you warned earlier about the danger of a misfit where you have you have a parameter that is the one that gives you the best fit to the observed experiments, but it may actually not represent the underlying biology or physics very well. And
right,
so here it seems to me that by insisting on D0, well, within the ensemble of model structures that you've made that choice every time, except in the second one. But you might not, if you can't, you might not want to force a choice of that kind of structure because you might, in fact, be forcing a misfit.
Yeah, so
Yeah.
I agree with that. So I believe ensemble models are a very good approach at making predictions. However, the point is that, so let's say you fit these models to your existing data, right? Imagine a situation where all four models fits your data quite well, but if you run it further, when you try to extrapolate, they diverge some point past into the future, right? Which means if you do an ensemble model, your uncertainty is going to explode past that point. But if you are able to tell, which one of these models are correct, you can eliminate one of them, then you can better control your uncertainty down the way. So I think even if you use an ensemble approach, it's still valuable to assign, have a way to assign better credit to these models.
I kind of disagree on the fact that it's like it depends on your design of the ensemble. So if you choose a design that doesn't fit what you're trying to reach, then yeah, but then again, you choose the ensemble. So therefore, if you choose the ensemble, you design the experiment, you can extract things the way you want them to, and you allow all models to live. It gives you much more than just selecting a model. The thing that bothered me is that you want to select a model. No, let them all live. Figure out later what happened.
Even if you let them all live, if your goal is to make a prediction, you have to be able to assign weights to these models.
This comes after. We disagree on this point.
I don't think there's necessarily as much disagreement here. What you're saying is that if you're going to do an ensemble point of view, you want to be able to reweight the ensemble based on your observations, which seems to me to be a reasonable thing to do. I think the philosophical question is whether you're trying to collapse to a single model structure or a very narrowly defined set of parameters, or whether you're willing to accept perhaps more uncertainty there. There's a question from Dinesh that is, how do you know when to activate control and when to turn it off? That comes back to your optimal experiment design that you started on discussing.
So the idea behind this slide, so for both situations, the idea is I don't know when to activate the control a priori, but rather I figure that out by optimizing for either parameter identifiability or the difference between two models, right? So this is the timing of the control is determined by the optimization process. So here, for example, from this plot, it shows me that I have two good candidates for the timing of the control, right? And in fact, in these two cases, they work about as well as each other. And in this case, the control is no longer a window function, it's more continuous, but it says I should, the solution of the optimal control says I should slowly ramp up my control until this point when I crank it up to maximum, stays there, and turn it off right near the end of the time period, right? So so the control timing is determined by the optimization.
Now you're assuming that you have a certain, now is this actually done on the space of all possible control functions, or are you assigning some limits to the allowed changes in the control function itself?
So the restriction here is that the control is bounded. I think it's bounded by 1300. And it has to be piecewise, I believe it has to be piecewise C1, right? So it cannot be some super high frequency jagged thing.
But if, for example, if I could have, say, a sinusoidal control function, and that would have been allowed, so that this is actually understood to be better than, say, a sinusoidal control function of some particular frequency.
Right, yes. So given the restrictions we have, this control is, so from the result of PMP, this is the optimal out of all piecewise C1 controls.
Great, that's very helpful. Other questions?
On your slides number 17, you're comparing the uncertainty of various parameter D, notch, gamma, and beta across different model. I'm just wondering why is that? Why not comparing the diffusion term in all models?
Yeah. And as for this slide, So the key here is not comparing between subfigures, but rather the comparison of the three curves within each subfigure, right? So the idea here is to see what happens to the identifiability of a particular parameter as the data resolution decreases, right? So for this D0, so in this simple model, we have the profile likelihood curve broadens out as we would expect, but it remains parabolic, right? Which means we retain parameter identifiability in this case. The key is that of these two other figures is that once I reduce the data resolution beyond a certain point, the profile likelihood curve for these two parameters are no longer parabolic, right? They become either something like this, and I cut the plot off here, but it just flattens out, which means the confidence interval of the parameter becomes infinite, right? Reminds you that the confidence interval is a portion of the number line such that the profile likelihood curve lies above the critical threshold, right? So here the confidence interval is 2-ish to infinity, right? So, and whereas in this picture, the confidence interval is now two disjoint pieces, right? One piece here and one piece here. So this is telling me that I have no idea if the parameter beta is around 0.5 or around 1.5. So the point of these figures is to illustrate how we can lose identifiability if we have fewer data. Thank you. And just to add, if we are comparing the same parameter across the models, so this figure does that. However, I would caution that the D0 in one model is not exactly the D0 in another model, right? They are both the diffusion coefficient, but if you they serve different roles, especially if you compare the porous fissure model to the standard fissure model, right? And in fact, I believe in this case, the D0 doesn't even have the same unit as this D0. So they are all diffusion coefficient, but they serve different roles. So compare them across the models is not very fair.
Thank you.
You raised a whole series of important points, which we need to think about more. You've shown how this works for models with a fairly limited number of parameters. If you get to more complex models where you have a very substantial number of parameters, how easy or hard is it to generalize, or does this methodology start breaking down when the models have too many parameters?
I think with more free parameters, the problem gets exponentially harder, right? So it's what people say the curse of dimensionality, right? You are exploring R n space where n is the number of free parameters you have, right? So it does get exponentially harder. To keep things tractable, one thing that I like to do when I have a hugely complicated model is that I fix most other, so let's say I have a cancer model, right? I have parameters for the cancer cells, parameters for the immune cells, parameters for, everything else. I'm going to say that I'm just going to focus on the tumor cell for now. I let the tumor cell parameters be free. I fix all the other parameters at a ground truth value. So that gives me something that's tractable to work with. It's an approximation, but I think it's one way you can make progress.
So you basically fit the submodels separately.
Right, yeah. So there are definitely problems with it, right? So if you just take slices of your likelihood landscape, that's not necessarily the exact best fit across the entire landscape. But if you do it submodel by submodel, you keep things tractable.
Right. I guess the problem with that is the example of your bimodal probability curves here where
Right.
there may be situations in which for one set of parameters in one submodel, there's only one possible outcome for the second one, but there in fact is some other pairwise set that would work that you won't see then, because you're
Right.
doing essentially a semi-local analysis rather than a global analysis.
Right.
And I'm not saying that this is easy. I'm not being critical about it. I just thought it was interesting to discuss that a little bit for the audience.
Hello, sir. I have a question. Yeah, so as you're talking about cancer model, suppose we have a disease model which have 3 to 4 variables, and there are so many parameters also. So if we get data for only 2 variables, suppose I have a system of differential equations having 4 equations, and I got the data for 2 variables, not the complete 4 variables. So what factors do we keep in mind to estimate the parameters now for now I have data for only 2 variables. So how difficult it is to estimate the parameters of this set of differential equations? And what things should I keep in mind to so that my parameters that I'm getting like are identifiable? So can you please share something on this?
Right.
Thank you.
Yeah. So I think a partially observable model is something like this toy example I have here, right? So in this example, if A and C are observable but B is not, then without redesigning the experiment, there's nothing you can do to comment on, what is B doing in the system, right? Because you cannot tell between these two alternatives. So this is a structural problem, structural non-identifiability in the model. However, if I have a different structure and you know a bit more about how these things are coupled, how the non-observable quantities are coupled with the observable quantities, then there is still hope that you can identify those parameters by observing the way they couple together, right? So even though, for example, B here is non-observable, because it has downstream effect on C, if you can somehow eliminate this arrow from in your experiment design, then you would be able to say something about B by observing how C is behaving.
Thank you so much.
Okay, any other final questions? If not, I want to thank you again for coming. I'm looking forward to hearing more about this as things develop. I'm sure at Duke you'll find lots of interesting ways to apply these ideas. And I will look forward to seeing people in a few weeks in July for our next meeting. Thank you, everyone.